Welcome everyone. Thank you for joining us. It's a great pleasure for me to introduce our speaker today, Mrs. Minakshi Kumar. She is a scientist G at the Department of Photogrammetry and Remote Sensing in Indian Institute of Remote Sensing. We welcome you, ma'am.
Thank you.
This session is all about the basic concepts of the image processing and image enhancement technique. And this is a subject in which we should all be deeply interested because the processing and the interpretation of the raw data is a prime requirement for the users. So, if you have any query during the presentation, please raise your hand in your control panel. We have the question answer session at the end of the presentation. Now, without further ado, the space is over to you, ma'am. You can start. Minakshi, ma'am.
Yeah, thank you. My screen is shared.
No, ma'am.
Not
Your
yet?
video, not yet.
It's a real pleasure to interact with you in this faculty development program being organized by GIS Bilaspur. I first of all thank the coordinators for giving me opportunity, and it is a pleasure for discussing this session on digital image processing, and mainly we will be focusing for the Earth observation data. You know, image processing has had its roots from the medical image processing, X-ray imaging, signal processing, but we would be mainly focusing on image processing applications or image processing for Earth observation data. The Earth observation basically comes under the umbrella of geospatial technology or geosmatics, which is basically the discipline of gathering, storing, processing, delivering geographic information, or basically you can say spatially referenced information. It encompasses many fields, and mainly three: remote sensing, GPS, and GIS. And I believe remote sensing session you had already in the first session. You will be subsequently having, I think, sessions on GPS and GIS. So in the remote sensing session, you must have been familiarized with the different platform and sensors that we have for Earth observation data. There are a large number of platforms. I have tried to list here only few Indian capabilities, like for the Indian capabilities for land and water Earth observation system has ResourceSat series of satellites, ReSat series of satellite, very high resolution satellite series. We have Cartosat and the new series of, again, Cartosat and very high resolution satellites. We also have a series for monitoring oceans through OceanSats, and a large number of, again, constellation of satellite for weather and climate studies. Our capabilities are from measuring a area as small as 0.6 meters to 1 kilometer pixel size. And there are a large number of series, satellite series in different categories, again in the pipeline, which are to be launched. So basically these series which we have earlier, like in the earlier slide I showed, we have capabilities from 1 kilometer spatial resolution to 0.6 meters spatial resolution, and 0.25, 0.3 is still a little bit in pipeline, which we'll be having soon.
We can't see the slides, ma'am.
You can't? Again, I had shared. It is showing me shared slide shares. If I stop sharing, I see you all. And
Ma'am, please reshare.
yeah, I'm just trying to share it again. Is it visible, the slides?
Yes, your first slide is visible, madam, but digital
now it's visible.
Yes, it is visible.
Yeah, we can see the first slide, but now I think we need to have a full slide presentation. As such, it's fine. It's
yes. Okay, let me just close all the other windows then.
Ma'am, just put your slideshow full screen.
Yes, I have done that only. Slideshow only. This is a slideshow mode. How is the presentation now? Because I cannot visualize. It is in full slideshow.
Ma'am, I think I think पहले presentation में you do the full slideshow mode, and then you select only that window. I mean.
Ma'am, you do one thing, you share your screen. In spite of sharing a particular window or something else, you share your entire screen.
Okay. Is it good? Can you see the slide?
Slideshow नहीं दिख रहा है, ma'am.
It is not in full screen, madam, actually.
Yeah, I did that only. Enter full screen. I think I have maybe having 2 windows of Microsoft Team or what? Can I disconnect and connect again?
Yes, ma'am. Ma'am, it would be better you reconnect.
Sessions that you had in the morning, a remote sensing background, and the session on remote sensing that we are familiar with terms like resolutions, and we are familiar with the different satellites and sensors which are launched, especially by the ISRO under different land and water, ocean, and weather climate series. So that session already was there in the morning for you. This slide we were discussing, but I think due to time limit, we should skip it. This also must have been discussed that we have various high resolution, medium, low, and ultra high resolution series satellites for gathering different kind of information, very high resolution, very detailed information to low spatial resolution for global level studies. So I should come back to my topic on digital image processing with the prerequisite that we understand what is optical remote sensing, what is electromagnetic spectrum, and mainly our session will be focusing on the visible portion of the spectrum, that is, and the optical remote sensing visible and the reflected infrared portion of the spectrum, which I think earlier Dr. Hina has given you an idea on visual image interpretation. So coming to digital image processing, we should first understand what is an image. Right? An image basically is a pictorial representation of an object or a scene. There are 2 forms of images, analog image and digital image. Analog image, as you understand, analog is for referring to the continuously varying quantities. So the images where intensity is displayed, like for example, this imagery which I have displayed here, it is a satellite image captured in digital mode. But what we are displaying here is the continuously varying quantity, which is intensity. Objects which are bright are white here. Objects which are not reflecting more energy are darker here. So this is continuously varying quantity. In contrast, when we have to study digital image processing, digital images are captured by the charge coupled devices, CCD arrays, linear array, area array kind of devices. And a digital image is made up of numbers. Like here, what I'm showing is a hypothetical image. So a digital image is made up of numbers arranged in a matrix form. In context of remote sensing, the rows are called as scan lines because they are captured along the motion of the satellite, and columns are captured as the detectors on that one line of the CCD array or a linear array on the sat. Now, the range of values depends upon the radiometric resolution, which must have been discussed in the first session, and the size of this pixel corresponds to the spatial resolution of the satellite sensor. Normally, single layer images, as have been shown here, in display, they are panchromatic in nature. That means they are grayscale images. And normally, the panchromatic mode, when the satellite is captured in a single broad spectrum, it is high resolution. But remote sensing data, multispectral remote sensing data, is captured in many different spectral bands. It is many spectral different bands for the same area. That means same number of rows and columns. And we utilize the portion other than what we can see, like ultra rays, gamma rays, infrared rays, right? And we can display them and have an interpretation key for those elements of for those multispectral images. Like here, a false color composite of the same image which was shown in the previous slide, and chromatic image. So this is the multispectral composite FCC of the same area. Advantages of multispectral, I think Dr. Hina must have discussed in our session. Right. So this is again a slide showing you that though what we see here is the visual representation of the satellite image, in background it is captured, it is in digital mode. So it is made up of numbers. So this is an image from Indian remote sensing satellite, IIRS-1 being this two image of an area which is nearby to Dehradun. And this is the visual, the satellite has 4 different spectral bands. The ranges are mentioned here. And this is the false color composite of that same image. A false color composite is when we display infrared on red, the red on the green, and the green on the blue band. The composite which is generated is called a standard false color composite, and an interpretation key has been developed for it. Yes, ma'am, any issues? For this standard false color composite. But any composite, if I display like infrared on red, red on green, green on blue, I get the false color composite. But if I have a combination in the image where I have captured the red, green, and blue, and if I display it, I will get a true color composite. But you must have been told in the remote sensing session that since the blue wavelength is scattered more, the lower wavelengths are scattered more, the most of the satellites are not recording the pure blue portion. They start somewhere from 0.45, which is the blue-green, 0.45 to 0.52, that is blue-green region. And that is why we don't get the true color composite. Whereas, whenever we take photographs or images from our mobile cameras, digital cameras, we are getting the true color composites because there the separation, there is the, it's using the pure blue wavelength also for capture. Now, methods of interpreting a digital image. There are 2 methods of interpreting an image, visual image interpretation and digital interpretation. That is now, I'm discussing about the interpretation both for the analog image as well as the digital image. An analog image has to be definitely interpreted only visually, whereas a digital image, once you have its analog representation, once you display a satellite image, we can do a visual interpretation of the satellite image. In addition, we can do digital image analysis and digital classification of those satellite images. Now, for visual interpretation, we can normally extract objects like we are trying to interpret what is this object, that is maybe house, or what is this object, maybe a car. But in image, digital image processing, when we have the satellite represent digital in digital form, then we can classify each pixel. For each pixel, we can say what is the land use or land cover category, or what is the object. In contrast to visual image interpretation, where you are trying to specifically focus on certain objects and trying to judge their significance. Right? So that is visual image interpretation, where you are trying to examine objects and try to judge their significance. For visual image interpretation, we use the various elements of interpretation like shape, size, tone, texture, pattern, shadow, association, etc. Like, for example, the image that I have shown here, maybe it's from an oil refinery or a soil storage depot, because what I see here is a circular tanks, right? So that means I'm associating a shape with it, and there is shadow, that means they are heighted objects, right? So there are large number of such storage tanks, such oil storage tanks. So maybe it's a refinery or a oil storage depot for me. So these we use different pattern, different elements like shape, size, tone, texture, etc. Association for interpreting these. So I think this visual interpretation session was there earlier before me, so I will not go into this. And now let's come to what is digital image processing. So we have seen in that earlier slides that digital image is made up of numbers arranged in a matrix form. And these numbers depend upon the radiometric resolution of the sensor. They depend upon the radiometric resolution of the sensor. So then, digital image processing, in simple words, can be defined as the computer manipulation of those digital values, the computer processing of those digital values which are there in a remotely sensed data, mainly for three main objectives. First one is image correction, second is image enhancement, and third is feature extraction or information extraction. So these are the three main features, three main functionalities and image processing, digital image processing software should provide, or these are the three major functionalities which, when we are interpreting a digital image, when we are processing a digital image, we must carry out these three processes. That is, correcting an image, enhancing the image, and information extraction. So the three steps, the first step, that is correcting an image, it includes removing of any noise, any geometric or any radiometric error that is introduced in the image, either during the acquisitioning by the satellite, or during the recording, or even during the time that it is being transmitted to the ground station. So number of errors can creep into our digital images, and the first step always should be identifying those errors and removing them. The second step is an optional step, which is image enhancement, which I say here, that is, it alters the visual impact of the image on the interpreter to improve information content. That means this optional step is only for visual image interpretation, because the computer can make use of that, whatever be the range of digital values, to make decisions. So the third step, important step, which everyone wants to use, is the information extraction step, which basically utilizes the decision-making capability of computers to recognize and classify pixels based on their signal. So these are the three. Yes. I am on slide number 12. Shall I in digital image processing, which any digital image processing software should provide? So the first one is removal of all kind of errors. including the radiometric and geometric error correction. Second is image enhancement. Third is information extraction. In addition to these three basic functionalities, any digital image processing software provides other optional steps like processing the photogrammetric data, microwave data, thermal data, hyperspectral data, and also integrating with GIS software. So now we will see these three basic steps, that is the removal of all kind of errors, enhancement and information extraction one by one. Okay, before proceeding further, there are a large number of tools, there are a large number of softwares which provide these three basic functionalities. There are commercial softwares for which we have to pay a license fee. Like, for example, ADAS Imagine is very popularly used for training purposes, image and like a photogrammetric suite is integrated with ADAS Imagine now for photogrammetric data processing. There is NV, there is EDRISI, ER Mapper, and so many different softwares, all licensed softwares for image processing. Then if we search on the net, that we will find a large number of free and open source tools for image processing. I have been only able to list here few of them because otherwise the font size becomes small. If we search on the net, we will find 10 best softwares for image processing and so on. So I have listed a few. ILVIS, which is Integrated Land and Water Information System. This was developed by Netherlands. Earlier, this was also a commercial software, but then from 2007 also they have made it freeware, ILVIS. Then there are other like Optics, GRASS, OSIM, Multispec, CVIP tools, SkiLab, that is counterpart of MATLAB, which is a very popular with the engineering colleges for image processing. So SkiLab is the free open source version of MATLAB, and so many different open source software which are available for doing these tools. Plus, if you are in the engineering colleges and you are familiar with processing, with programming, then you can write your own codes using any Python or any Java or any high-level programming language that you are familiar with. Large number of now open object-oriented programming languages which are very convenient to do image processing. Simple codes and all are available. So now coming, as I said in the previous slide, we will see the three components of the image processing one by one. The first one is removal of all the errors. So this removal of all the errors, this step is called as image pre-processing, right? Why this step is necessary? Because, remote sensing systems, that means remote sensing systems, what I mean is satellites and sensors. Sensors are doing the recording and they are launched onboard these satellites. Satellites are orbiting around the Earth. So this combination of remote sensing systems, platforms and sensors, they do not function perfectly all the time. They function perfectly, but sometimes they may go out of calibration, they may drift. So once an image is there with some error, it has to be removed with the pre-processing operation. So pre-processing operations are the image restoration and rectification, which are to remove the sensor specific errors and the platform specific. Any error? Any issue? I can hear the mic, or it's somebody else, I think. Screen. Other mics, yeah. Okay.
So
yeah.
Pardon?
Pardon?
You may continue, ma'am.
Okay. So the two most common type of errors which are there in the remotely sensed data are the radiometric errors and geometric errors. Radiometric errors, they are the errors in the radiometry, that is the pixel value. When the DN value or the pixel value, radiometric value gets distorted, it's the radiometric error. And when the location of that value, the shape of the pixel is distorted, it is geometric error. So the different kinds of radiometric errors which are there in the imagery, they are periodic line and column dropouts. So here, like for example, I'm showing here few dropped lines. Dropped lines basically mean that when the sensor either fails to record, it goes bad and it fails to record. So there is a dropped line. Dropped line means a line which has value of 0. So it will appear as a black line as here in the second picture here on the first row. Then the column dropout will be in the columnar mode. The line dropouts will occur in the sensors like Landsat, where they are recording in the whisk broom mode. And column dropouts will be in the sensors where they are recording in the push broom scanning mechanism. So if the line is dropped, either the sensor goes bad, the detector does not record, or during transmission, the line is lost, then the correction has to be done, because these black lines will interrupt with the visual interpretation as well as with the digital analysis. So the correction method for such lines would be that we have no option. If a line is dropped, you cannot artificially generate the data. You cannot have that data back, but we can artificially generate it by replacing it by either the preceding line, replacing it by the succeeding line, or we can take the average of the preceding and the succeeding line to fill in the DN values, with the assumption that obviously the data, the reflectant doesn't change by a large amount because it's the same feature. Then in contrast to line and column dropouts, there is line and column striping. You can see here white banding patterns. Again, this may be periodic or non-periodic. That means here the detector does not go bad. It doesn't fail to record, but it goes out of calibration and it starts giving the higher response or lower response. So, of course, on board there are calibration mechanisms and they bring the detector back to the calibrated value. But once if there is an image with stripes, you correct it with the histogram matching method. That means you choose a detector which has no error and you match the faulty detector, the one which has these stripes, and you correct them. Or we correct it with the sensor gain and offset methods. Then there can be random black and white pixels here, like for example here. So these random black and white pixels, they are corrected by filtering. And what is filtering, we will see in subsequent slides. Then there are atmospheric errors, like you must have been told that the lower wavelengths are scattered. When the lower wavelengths are scattered, the image is captured with the haze. So removal of those haze errors, like dark object subtraction, is the correction method. And this is one of the atmospheric error. Other kind of atmospheric errors which are there is when the two images are captured with different sun angles. That is, they are captured at times when the sun angle was different at the two scenes, and that you have to make mosaic of the two scenes. When the two images have to be independently processed as if sun was overhead, and then remove the sun angle effect and then mosaic the images. So in all these errors, the DN value, the radiometry gets affected, and these are called as radiometric errors. The DN value gets affected. Now, when the location of the pixel gets affected, it is geometric error. That means the shape of the pixel gets distorted. Now, shape of the pixel can get distorted due to number of reasons. Like, for example, when the area is very large, the earth curvature effect is visible. So the pixels at the center will be perfectly square, and the pixels in the corners of the imagery will be elongated. So these are kind of geometric errors, and the other geometric errors can come due to the sensor or the satellite attitude and the role which you're being deformed, the altitude rising and dropping. So the pixel shape can get distorted. Now, even if there is no geometric error, what happens is whenever you have a satellite image, you want to overlay it over topo sheet. So even if there is no geometric error, whenever you want to overlay your image over a topo sheet, or you want to have a ground coordinate system associated with it, then you need to do this step, which is a common step for removing the geometric errors as well as overlaying my imagery over the map or topo sheet. Or you can say with the help of a GPS, we refer it to the ground. Now, even if there is no error in the geometry of a pixel, whenever I want to transform my image so that I transform it to a particular map projection or to a particular scale, this step is also called as geometric correction or rectification. Now, this step is necessary whenever I want to use my image as image map. So I use a map to make an accurate area, distance, direction measurements. So whenever I want to make these measurements from the imagery, I need to do the step called as rectification. Now, these are two different grid systems. One is an image grid system, which is arranged in a matrix form, which has addresses in terms of rows and columns. And there is another grid, which is map grid. And map grid is in a certain map projection. It has certain northings and eastings associated with latitude and longitude associated. So there are two grid systems. So rectification is achieved by transforming data from one grid system into another grid system using a mathematical transformation. So whenever I wanted to overlay this image over a topo sheet, there were four differences in geometry that we want to remove by this geometric error correction. The four differences in geometry is that if I'm trying to overlay my image over topo sheet, their origins may not match. The origin of topo sheet and origin of the map may not match. So the image has to be translated or shifted to fit over the appropriate area. Then there is the second thing is differential scaling. The image has to be either compressed to fit over the topo sheet, or may have to be expanded to fit over the topo sheet. It depending upon two things. One is the resolution of the image, and second is the scale of the topo sheet. It may have to be expanded or compressed. Third is my image may not lie perfectly rectangular. It may have to be rotated to fit over a particular. And fourth difference is geometry is the shear, which is basically offsetting of each line to the west. This is due to the Earth rotation, right? Because when the satellite is moving, as soon as it captures one line of information, it goes to the next line. The Earth has rotated underneath, so it is not only few meters; it is few kilometers that. Few to 1,000 kilometers, depending upon the different swaths and different resolutions, that the line has to be pulled to the. So these are the four differences in geometry between the image and the topo sheet, which has to be removed, right? Even if the shape of the pixel is perfectly good. So this step is called as rectification or geometric error correction. So there are basically two strategies when I'm having the image and I'm trying to fit it over a map. In this step, what I will do, I will find ground control points. I will find certain pixels in the image. Ground control points are those pixels in the image for which I know the ground coordinates accurately, either through the topo sheets, through the maps, or I have a GPS and I can go to the ground to get the coordinate of that point. That means a pixel for which can be very clearly identified in the image as well as on the ground or on a topo sheet. So its first requirement is that I have a ground control point and I'm overlaying that image over the topo sheet. The second strategy is that I have two images. I'm not concerned with any map, but there are two different satellite images or any two different images which I want to overlay one over the other, So these are the two strategies, and the rectification process is a two-step process. The first step is the grid transformation, where I use a polynomial equation to transform the pixel coordinates to the ground coordinates. And here I use ground control points, a minimum of 4 ground control points for first order transformation. In fact, for first order transformation, we need only 3 ground control points, but to check the accuracy of transformation, we need at least 1 more ground control point. So I use a polynomial equation to transform where a pixel would lie on the ground, and vice with the same ground control points, I can do vice versa. That means where a particular map pixel would lie on the image. So this way, the first one is only matching the coordinates. The second step here in the rectification step is to assign DN values to the new position, to the rectified position. So these are two steps in the rectification, removing of the geometric errors. So actually here, in the schematic here, I'm trying to show that in my input image, I identify 4 ground control points. So points for which can be easily identified on the image and on the ground, and transform this to the map coordinates using a polynomial equation, and least square fitting technique. So you need not worry about these the mathematics behind. It is the software which will take care. We only need to identify the ground control points. Now, ground control points, it's very critical for the accurate rectification that I have accurate ground control points. So my ground control points should be those points which are very well and very clearly identified on both the topo sheet as well as on imagery. That means we should take those points which do not change over time. That means any regular feature, any man-made feature like road intersections, corners of buildings, corners of airport runways, towers, which can be which have very well-defined geometry and which do not change over time. Those are the preferable points. But those points will be visible only on the very high resolution image. But what if you are doing studies like here in the medium to low resolution imagery? There you have to take larger features like river bends, distinct natural features. But again, we should take care that we should not take those points which change over time. Like if I'm taking a tip of a forest as a ground control point, the tip may have been clear. Somebody may have cut the forest. So that tip is moved, or afforestation is done and the forest has grown and now the tip is a different location. So we should take care that we should not take those points for ground control point which change over time. And depending upon the mathematical equation, we require certain minimum number. And as I was mentioning, for the first order transformation, I need a minimum of 3 plus 1, that is 4 ground control points for checking the accuracy. So here it is shown an example that in the image, I identify a pixel that is like here, for example, corner of a clearing in forest, and it's a reserve forest, so it doesn't change. So here the same corner is identified, the corner of the road and canal intersection and so on. So I mark such points and do the mathematical transformation using the first order equation. So I can calculate where a particular pixel would lie on the map and where a particular map pixel would lie on the image using these four set of ground control points. And how accurate is my transformation that we see with this error, which is called as root mean square error. So root mean square error, generally an average RMS error of less than half a pixel, 0.5 is acceptable, and per ground control point less than 1. Average less than 0.5 and per ground control point less than 1 RMS error is acceptable. Then once the transformation is done, once these equations are calculated, then in the next step, we need to fill in the DN values. We need to assign, because now the imagery geometry grids have changed. There was an original grid with the numbers, and now I have calculated a new grid corresponding to the original grid. And I need to fill in the DN values in this grid. And this step is called as resampling. Once I have warped the image, I need to fill in the DN values. And this step is called as resampling. There are three basic strategies again for filling in the DN values. The first one is the nearest neighbor, like the grid pixel which I need to fill. Like for example, here the light gray pixel. It is nearest to this previous nearest to this dark gray pixel in the previous image. So the first strategy is assign the nearest pixel to the new pixel location. The second strategy is bilinear interpolation. For the light gray pixel, take the 4 nearest pixels to them and find a weighted average of the 4 nearest pixels and fill in the output gray. That is what I written here. Bilinear interpolation assigns a weighted average of the 4 nearest pixels. And the cubic convolution takes the weighted average of the 16 nearest pixels. As I've shown here, it takes the weighted average of the 16 nearest pixels to fill in the DN. So once I do these two steps, mathematical transformation and resampling, my original image, which only had rows and columns like here, now it is transformed into a north-south oriented map. Each pixel has a ground coordinate associated with it. So this is the step which is called as image rectification. And in doing this step, any geometric error, if it was present in the imagery, will also get modeled and will be removed. Because now the image is oriented according to a north-south oriented map. It has a northing and a easting. It has a latitude and a longitude associated with it, and the DN values also, in addition to the rows and columns of the original system. That is, from the original system, I have a new grid which is having the geometric coordinates also along with the rows and columns. So this is the first step, that is image restoration, where we remove all kind of geometric and radiometric errors. The second optional step which I told you was image enhancement, where we only change the image so that it is easier to visually interpret the image. So that means all the enhancement operations are modifying the DN values so that the image becomes more interpretable for a particular application. That means I'm accentuating certain features for visual image interpretation. Now, since I'm enhancing, but I'm basically changing DN values. So these DN values change can be categorized as point operations, local operations, or multi-image manipulation. Point operations are those where I change the DN value, where I change the brightness value independently according to some mathematical, statistical, trigonometrical criteria. Very popular is contrast enhancement here, which we'll be seeing in the subsequent slides. So first category of enhancement is contrast enhancement or point operations where we are modifying the DN values. The second category of enhancement is local operations, where a particular pixel value is changed, it's modified based on its neighboring values. So the difference is now the point operation, each pixel is changed independently, but according to some mathematical, statistical, trigonometric criteria. In the local operation, that pixel value is modified based upon its neighboring values, based upon its spatial neighbors. And there is third category of enhancement, which is called as multi-image manipulation, whereas basically the one pixel value is modified based on its value in different bands. That means the point and local operations were single band analysis, and multiple band analysis is another category of enhancement. And ratioing principal components come under this category, which will be seeing them one by one. So first we will start with the image enhancement, contrast enhancement. So for that we should first understand contrast. What is contrast? Now contrast, the best example is most of us, in fact I think all of us must have gone to a movie theater at one time of our life. And we see that whenever we want to see a film, the screen is very well lit and we, the audience, are sitting in the dark. Why? To have a best contrast between the screen and the background, right? So screen is well lit. Same contrast we can have in our image. Only thing is, in image we are having numbers. Image is made up of numbers. So the contrast can be defined as ratio of maximum intensity to minimum intensity, and in image it will be corresponding to the DN values. The ratio of maximum intensity, maximum DN value to the lowest DN value. And suppose my monitor can display values between 0 to 255. So when my image is having values from 0 to 55, like which I'm calling is original, so there is good contrast between the dark and the bright objects. I can see the riverbed, I can see the agricultural lands and the dark forest, right, in this particular band. Because the full range of display devices used. In contrast, here you can see this is a low contrast image, a dark image, which is only using the only half portion of the display device. And this is very bright image, a saturated image, which is only using the upper portion of the display device. Right? It is, this one is from 0 to 127, this one is 127 to 255. So both the low contrast and the saturated images are not well interpretable, and our optimum contrast requirement is that my image should have DN values between 0 to 255. So if the image is not having those range of values, like for example here, this particular image had values from 84 to 153, not between 0 to 253, then the technique, the mathematical technique, or is the point operations or the enhanced contrast enhancement, where I expand this original input values to make use of total range of display device. So density values are pulled apart, that is expanded over a greater range. The minimum value is assigned to 0, the maximum value is assigned to 255, and all the DN values in between are linearly distributed. So this will enhance my image. It will make my objects more interpretable. Like for example here, this was a satellite image having values between 12 to 43, a very narrow range of values, and objects were not well interpretable. When they are expanded between 0 to 255 using a linear transformation, all the objects become very much interpretable. We can see the small land masses also in the water body, and within the land also different category of objects, how they are reflecting, become enhanced as compared to the left image, which is not enhanced. So this is linear contrast stretch, and there is a non-linear contrast stretch. Right? The non-linear contrast stretch is histogram equalization, where we are trying to equalize the histogram. That means all the gray levels values, all the DN values in the image, they have same frequency. They have same frequency. Like for example, here, the same image which had values between 12 to 43. And now I'm equalizing the histogram. That is, all the DN values have near about same frequency. So the enhancement is more in the peak region. Right? So this is a non-linear enhancement category. If we compare the linear stretching and the histogram stretching, both are used for overall contrast enhancement, like here linear stretching and histogram equalization, as contrast to the original unstretched image, which has very narrow range of values. The linear stretching will simply expand it between 0 to 55. Whereas the histogram equalization will change the shape also of the histogram, and it will enhance the most populated range. That means wherever the peaks are there. Right? So the histogram equalized image appears to be more contrasty than the linear stretching image. Then the second category of enhancement is local operation or filtering, where the pixel values are modified based on the surroundings. Now, filtering in image processing has an analogy to our daily life. In our daily life also, we use a lot of filters. We use a water purifier, a water filter to filter out the impurities and have pure water drinking water. We use a sieve to filter out our tea. Then what we are doing there? We are blocking the tea granules, allowing the tea to flow through in our cup. So that means basically we are suppressing certain information and we are allowing other information to pass. Same thing can do in the image also. We can suppress certain frequencies and we can allow other frequencies to pass through. So there are in the image, actually there are two kinds of details which change very gradually. These are called as low frequency details, and these are the same land use category. In contrast to low frequency details, an image may also have high frequency details, which is a sudden change in the DN value. So I can use filtering method to block one of them, either low frequencies or high frequencies. So low pass filters are designed to block all these suddenly varying components, and the low pass filtering is done to smoothen the image. They are basically used for removal of salt and paper noise. In doing so, it also causes blurring of image at the edges. High pass filters, they remove the slowly varying components and they only preserve the high frequencies. They are basically used for edge detection and edge analysis. So low pass filters, as I mentioned, they will smoothen out an image, they will remove all the errors, and they are implemented as a moving average window concept, where the average of a window is computed and placed in the output. Right? So high pass filters, as I mentioned, will only detect edges, boundaries where transition is taking place from one category to another. So high pass filters also can be done in direction mode, omnidirectional, like here, where all edges in all directions are detected, and in particular direction also, when you have a particular geological features or different infrastructure features, you want to enhance this, you can also do the directional filtering. Then the third category of enhancement is multiple band cooperations, where you use more than one band to extract certain meaningful information. And the spectral ratioing is the most commonly used, the multi-band operation. This one removes the variations in digital values due to variance in seal elimination. That means maybe due to different topography or different illumination, scene illumination, there are different values which are coming for the same object that can be removed using the ratio. It is very useful in the vegetation studies, mineral studies. Now, basically, ratio images means we are dividing one band value by another band value on a pixel by pixel basis, not an average. Pixel by pixel basis, we divide one band values by another. And as I said, it is very commonly used in the vegetation studies or extracting certain minerals. So like for example, in vegetation indices, what is the proportion of vegetation present in a pixel? That is a vegetation index. How much percentage of vegetation is there in a pixel? That can be computed. There are a large number of vegetation indices which are available in literature. You can see they are ratio vegetation index, normalized differential vegetation index, and so on. So ratio vegetation index, basically this utilizes the spectral reflectance properties of vegetation. In the previous session, Ms. Sinha also must have told you that vegetation reflects infrared very highly. It has high reflectance, like for example here, 50% of the vegetation is being reflected in the near infrared, only 8% in the visible portion of the spectrum. So when we take the division of infrared band by the red band, this here output you can see the RVI, this will highlight vegetation, right? Because a high value divided by the low value, the ratio will be much higher, and whatever is the output, white pixels will be vegetation, right? And a very popular estimation of vegetation is this normalized difference vegetation index NDVI, which is infrared minus red divided by infrared plus red. Right? And this can highlight, in fact, the difference between the healthy vegetation and the sparse vegetation or the unhealthy vegetation. Because there, when you have healthy vegetation, there will be more difference in intensity between the NIR and visible for the thick and healthy vegetation, and there will be less difference like here, which is shown here, between the intensity of the NIR and visible for the sparsely vegetation or the unhealthy vegetation. So this vegetation indices are very good approximators for vegetation index. And in fact, the vegetation cover map of India, the forest cover map of India is also being prepared periodically using the vegetation indices. Like Forest Survey of India earlier, as I remember, they were doing it every 2 years using the satellite remote sensing data. How much is the percentage of forest cover in India? The 2-year annual report was being published using NDVI and the satellite data. So similarly, you can have large number of indices. You can have indices for different minerals, for different rocks. And like here, the one more example which I've given here is for water. There can be snow index, there is snow index, there is water index, built-up index. So basically, it is utilizing the spectral reflectance properties of water, of vegetation, of different minerals, of different snow, and so on. And wherever there is a maximum slope between the two bands, they are subtracted to get an index. Now, the second category of multi-band operation is image fusion. This image fusion is again an optional enhancement step because now you know this since last 2 decades. Most of the satellites, the land satellites, they are operating in 2 modes, multispectral mode and panchromatic mode. Panchromatic mode has a broad multispectral wavelength. That means it's basically in the visible portion of the spectrum, a broad wavelength, typically equivalent to a black and white photograph, but it has high spatial resolution. The multispectral mode has better spectral resolution because there are a large number of bands in the multispectral data. but its resolution is normally poorer than the panchromatic. And the human nature is, I want best of both the worlds. I want a high spatial resolution and a high spectral resolution. So if the satellite cannot provide me, I can do some mathematical techniques to have high spatial and high spectral resolution. That means multispectral data I can have in high spatial resolution also. So this step is called as image fusion. So the earlier image which I had shown you here was panchromatic image at 1 meter spatial resolution. This is the Dehradun city center, the Dehradun Ghantaghar area with Gandhi Park and Parade Ground, and the Ghantaghar area is here. Then its equivalent multispectral data, which is 4 meter spatial resolution. That means 1/4 of the resolution of the panchromatic. And I use a mathematical technique, Brouwer transform or multispectral technique or IHS transformation to combine the high spatial and the high spectral resolution. So these were the category of image enhancement. Now coming to the most important step, that is information extraction or image classification. Now, why we are interested in image classification? As an analyst, as an image processor, I may be familiar with doing image processing. But a user or a decision maker, a minister, who is only concerned with providing some relief and rescue operations while there is some flood or while there is some drought, some relief has to be given. How much is that amount which has to be given? So he doesn't know image processing, and he's not interested in my digital numbers. He wants a map. He wants a map if in a particular field that particular crop is there or is it destroyed, so that farmer can be given relief. Or if there is, it's a flood, so that area can be reached or not reached. So the user or decision maker is only interested in a thematic map. So then we use the computer's decision-making capability to automatically categorize pixels, and this step is called as image classification. So here we have spectral pattern classification. We are automating the land cover classification using pixel by pixel spectral information. Sometimes I need the spatial properties also, the location, proximity to a particular feature, the texture of that area. Then it is called as spectral pattern recognition. And temporal pattern recognition is when you are using at least 2 time images to identify a particular object. Like for example, if you are seeing the growth of wheat crop, so you have to have a temporal images to see how it is growing and estimating the land use of that. So the classification methods, right, normally use the combination of the spatial, spectral and the temporal method. There are basically 3 categories: supervised, unsupervised and hybrid for satellite image classification. We will see them. So then multispectral classification can be defined as assigning each pixel in a remotely sensed image a label describing real world object. That is automatically categorizing or automatically classifying all pixels in an image into one or the other land use categories. So output will be basically a form of digital thematic map. And as I said, there are 3 categories of classification: supervised, unsupervised, and hybrid. So supervised classification, as the name suggests, there is supervision. So the analyst is supervising the algorithm by providing some samples. So supervised classification, as I've written here, it requires training samples. So here the samples of known identity are used to classify pixels of unknown identity. So what is done for the samples that are marked, we calculate the multivariate statistics, the mean, median, the standard deviation, the variance, the covariance, the correlation for the samples. And all pixels, whether they are inside the samples or outside the sample, whether they are a known sample or whether they are unknown pixel, they are compared with the statistics of the samples. And wherever it is nearest, the statistics are matching of unknown pixel to the particular class, it will be assigned to that class. So this is supervised classification, like for example here. So this is an image where I'm providing training sites or samples, right? Samples now with training sites are the samples of a class. So then we calculate the statistics for these samples. So these training sites or these samples should be distributed over the entire image and not focused to a local area, because the local area may have some atmospheric disturbance. And training data should be preferably homogeneous. Okay? So then these training samples are marked and the algorithm is chosen, which will classify each pixel into one of these classes. Like for example, this particular pixel, it has classified as forest. This particular pixel, it has classified as water. So samples of known identity, samples are provided here and they classify all the pixels. No sample was provided here, but it classified it as forest. In contrast to supervised classification, there is unsupervised algorithm where the natural groupings of DN values are made, where an image is classified based on groupings of the natural pixels. Okay. Algorithm itself forms natural groupings or clusters in the image, and the information utility is assigned by the NLF. So the algorithm can only group a particular type of pixels that they are category A or class 1, class 2. Like here, example here is the previous method, this was classified as forest. But now the unsupervised algorithm, because there are no samples here, there is no supervision. So the algorithm has only grouped them together that these are similar pixels. But whether they are forest or non-forest, that the unsupervised algorithm cannot say, because it only finds the natural groupings from the natural clusters in the image. Then the next step after you have done classification is accuracy assessment. How accurate is our classified result? So that is done by comparing the classified image with the reference data. Now, reference data is the ground truth which we collect by going to the ground, and map labels are the classified images. So a matrix is prepared. In this matrix, the diagonal represents the correctly classified pixels and the off diagonals present the errors, the error of omission and error of commission in the remotely sensed data. The overall accuracy is the sum of correctly classified pixels to total number of pixels that you are using for testing. Of course, the entire image cannot be used for testing the accuracy of transformation. So a random sample is taken for a certain number of pixels, and their reference data versus the classified data is compared pixel by pixel. Okay, so then the next thing after we have done classification, though your syllabus had said only to cover till classification, but I thought change detection is very important application which must be done after classification. So I included them in my slides. So change detection is basically a process of identifying difference in state of an object or a phenomena by observing it at two different times. And that is our main purpose why we are doing remote sensing. Since the first satellite which has been launched until today, we have large number of satellite data which is available. And we want to see how the land use or land cover has changed over time and how this global change is impacting the climate change. Right? So for this purpose, the change detection is one of the very important application or one of the very important digital image processing technique which should be studied after the classification. Like maybe you must have seen our before-after images of like of this image I'm trying to show of Ghantaghar of FRI. before and after. That means at present and so on. So this is very important step. There are large number of techniques for change detection, but I have only tried to include here post classification. Once you do supervised classification, so for change detection, it is very essential. We understand that we should have at least 2 time images. So we classify the time 1 image and we classify the time 2 image and compare the land use maps and find out the change map. Right? This is one of the method of change detection. And change detection application, it finds its application in land use, land cover change, forest mortality, defoliation, damage assessment, deforestation, wetland change, forest fire. Very you can say important point in Uttarakhand, because we get a lot of forest fires every summers. Land to find out landscape change, urban change, environmental change, drought monitoring, flood monitoring, and so on. In fact, even also crop monitoring, shifting cultivation practices, and so on. So there are large number of applications of change detection, and I thought it was a very important topic which should have also been covered. So I included in my slides. And then only one case study I have tried to put here, though we have large number of case studies of different image processing applications like vegetation cover mapping, forest cover mapping, flood inundation mapping, etc. Different crop type growths. So I've tried to include here for the land use land cover change detection, which was done over approximately 20 years or more. Yeah. So from 1994 to 2017, the land use change, how it is affecting a particular district in Sri Lanka was carried out using 2 different type of classifiers. Once we used 4 different images: 94 image, 2001 image, 2009 image, and 2017 image, and mapped the land use land cover on those 4 date images spread over 20 years approximate. Then what was done was, with this historical data available to us and 2017 classified data also, we tried to model that what was the classified map in 2017. We had the actual classified map of 2017. We simulated a classified map of 2017 using a model, find out the difference, how much was my accuracy, and then simulated how the land use would be changing in 2030. So future prediction scenario, which is very important for seeing how the area has been changing and what is the future scenario in that case. So that study was also done using this land use land cover mapping. So with this, I have tried to cover an overview of image processing, which is a very vast topic in this short time. And that is all from my presentation. Now I can open for discussion or the queries.
Thank you, ma'am, for your very interesting and insightful